Okay, let's dive into one of the most elegant and frankly crucial concepts in high-performance computing. When you think about what makes a GPU so fast, you probably think of raw processing power, right? But the real secret weapon, the magic behind the curtain, it's something else. It's an incredibly clever system for managing data, an architecture designed to solve one massive, fundamental bottleneck. And it all comes down to memory, but probably not in the way you're thinking. Right, so before we get to the solution, we've got to really understand the problem. What is the one thing, the one major roadblock that's holding back even the fastest processors in the world? It's not the chip's ability to calculate. Nope. The real challenge is just feeding the beast. It's about getting data to it fast enough to keep it from sitting idle. And this right here is the heart of the problem. It's what we call the great speed mismatch. On one hand, you've got your processor, which can perform billions of calculations every single second. Think of it like a world-class chef who can chop and cook at superhuman speed. But then you have the main memory, the pantry, where all the ingredients, the data, are stored. And that pantry is hundreds of times slower. So what happens? The chef is just standing there, tapping their foot, waiting for ingredients. The processor is constantly stalling, literally starved for data.
So what do, right? If you can't just magically make the giant memory pantry as fast as the processor, and believe me, for various reasons you can't, what's the answer? Well, the solution isn't just about faster memory. It's about smarter memory. It's about building a clever, layered system, a hierarchy designed specifically to bridge that massive speed gap.
And that brings us to the architectural blueprint for this whole solution. This is what we call the memory hierarchy. Think of it as a pyramid, with different kinds of memory at each level, each with its own specific job. This is the real engine room, the secret sauce inside every modern GPU.
So let's build this pyramid from the ground up. At the very bottom, you have global memory. It's huge, it's vast, but it's slow. Think of it as a giant public library way off campus. Then, moving up, you get to the L2 cache. This is like a smaller central staging area, quicker to get to. Closer still, you've got L1 cache and shared memory. Now we're talking about a local workshop right next to the processor. And at the very top, the peak of the pyramid, are the registers. These are like a personal toolkit, the tools a single worker has right in their hands. And here's the key takeaway, the fundamental trade-off. As you climb this pyramid, the memory gets exponentially faster, but it also gets a whole lot smaller and scarcer.
Okay, so that's the big picture. Now let's zoom in and meet the individual players on the team, specifically the ones right there on the chip. These are the guys at the top of the pyramid, the high-speed crew that does all the real heavy lifting. First up, we have registers. These are, without a doubt, the smallest and fastest memory units you can get. The way it works is the compiler assigns a set of registers to a single processing thread, and they belong to that thread for its entire life. No other thread can see them, touch them, or use them. They are completely private. It's exactly like that personal toolkit, the hammer, the screwdriver that a worker's holding in their hand for the job they're doing right now. All right, next is shared memory. And this is where things get really, really interesting, because this one is different. Unlike a lot of other memory, this isn't managed automatically by the hardware. No, this is explicitly managed by the programmer. That means you, the person writing the code, have direct control. You decide exactly what data gets put in here. This control transforms it into a super fast, shared workbench, where a whole team of threads can work together, sharing tools and data, collaborating on a task.
And then you've got the caches, both L1 and L2. The best way to think of these is as smart, predictive assistants. They're completely managed by the hardware. Their whole job is to try and guess what data a thread is going to need next and fetch it ahead of time. So when a thread asks for something, the hardware goes, hey, let me check the cache first. If it's there, what we call a cache hit, it's a huge time saver. The entire purpose of their existence is to cut down on those painfully slow trips all the way out to the main memory library.
Okay, let's just put that all together in a quick spec sheet. You've got registers, the absolute fastest and smallest, managed by the compiler and totally private to a single thread. Then you have shared memory, also incredibly fast, but managed by the programmer to let the team cooperate. And finally, the caches, managed by the hardware, acting like smart assistants to cut down on those slow memory trips. Each one has a very distinct, very vital role to play. So that's the architecture. That's the what. But so what? What's the actual payoff here? Why did engineers go through all this trouble to build such a complex system? Well, this is where it gets really good. This whole hierarchy is designed to achieve three main things. First, latency reduction. Latency is just a fancy word for waiting time, so this drastically cuts down on how long the processor sits around doing nothing. Second, bandwidth amplification. This means you can get more data delivered to the processing cores every single second. And third, and this one is huge, data reuse. The whole idea is if you're going to need a piece of data more than once, you should only make that one slow trip to the library to get it. After that, you keep it close by in your fast, local memory.
And this chart, wow, this really drives the point home. Just look at these numbers. If a processor has to get data from global memory, it could be waiting 400 clock cycles or even more. I mean, it's just sitting there, burning time. But if that same data is in the on-chip shared memory, it could be as little as 20 cycles. We're talking about a 20x improvement. That's literally the difference between waiting for an overnight package to arrive and just reaching over to your workbench to grab a tool.
And this creates this incredible chain reaction, this performance impact chain. It all starts with the programmer. They have to design their algorithm specifically to reuse data. Then, they make sure to load that data into the fast on-chip memory, like the shared memory or caches. Because the data is right there, the GPU cores don't have to wait. They don't stall. And the final outcome of all this? Your application runs way faster. And, as a really nice bonus, because those long trips to main memory burn a lot of energy, your GPU actually uses less power. But here's the catch, and this is probably the most important point of all. Getting this amazing performance, it's not automatic. The hardware gives you this incredible potential, but it's the programmer's job to actually unlock it. To get that peak performance, you absolutely have to play by the rules of the road.
And this quote really gets to the heart of what that means. It's not enough to just say, okay, I'm going to use shared memory. No, you have to arrange how your threads access that memory in a very specific, very careful way. They need to be coordinated perfectly, because if they're not, you can run headfirst into a problem that completely kills your performance.
And that big problem has a name. It's called a bank conflict. Okay, so to get this, you have to realize that shared memory isn't just one big block of data. It's physically divided into a bunch of smaller modules called banks. The perfect analogy is to think of it like a grocery store with many different aisles. This setup is brilliant because it allows lots of threads to grab data at the same time as long as they're all in different aisles. A bank conflict is exactly what it sounds like. It's what happens when a bunch of threads try to cram into the very same aisle at the exact same moment.
Let's put it in simpler terms. Imagine you have 16 workers on a construction site, and they all need to grab a specific wrench from the same drawer of the same toolbox at the exact same time. It's just not going to happen, right? They can't all reach in at once. They have to form a line and take turns. That's what we mean by serialized access, one after another. And just like that, poof, your massive parallelism, your huge speed advantage, it's gone.
So how do smart programmers get around this? How do they maximize data reuse while avoiding these conflicts? Well, one of the most powerful and common strategies is something called a tiled algorithm. The idea is actually pretty simple. You take your huge problem, your massive data set, and you break it down into small, bite-sized chunks called tiles. Each tile is small enough to fit completely onto that fast shared workbench. So the whole team of threads works together to load one tile onto the bench, they process it completely, and only when they're done do they go fetch the next one. It's incredibly efficient.
And all of this brings us to a really fascinating question for the future. On one side, you have these incredibly smart automatic caches that are getting better and better with every new generation of GPU. On the other, you have this programmer-managed shared memory, which gives you the ultimate control, but also adds a lot of complexity. So the big question is, as the hardware keeps getting smarter, how much longer will programmers really need to be in the business of managing all this memory by hand? It's a fundamental tension, and the answer to that question is really going to shape the future of computing.